Welcome back to the Ephemeris podcast. I'm your host, Felian, and I apologize for not having this episode out on time. I talked a little bit about that in the post, but hopefully you all do not mind the slight delay in some of these podcast episodes recently. I've been keeping myself pretty busy, so yeah, when things don't work out the way I want them to, the podcast episodes won't be able to go out when I want them to. So um, I still try to get these out on time for you all. And anyways, we are here now. So today's episode, we're going to talk about 3 more articles. We're into the 5th episode of the new chapter, the new season. So if you've been here a while, you are already familiar with the format of these episodes. If you're not, welcome. We are happy to have you here. So the first article we're going to be talking about today will be about an oceanic exoplanet that we've discovered and a little bit more in-depth stuff about exoplanets in general. We're going to move on to our second article, which is going to be about Betelgeuse and some of the weird occurrences that have happened in the past few years with the star. And the last article of the day will be hydrogen poor core collapse supernova. So let's get right into this thing. We've talked about exoplanets before, and that was on the Fulton Gap episode. But we'll quickly recap the 4 types of exoplanets that we have discussed so far. We've talked about super Earths, which are rocky worlds larger than ours, Neptunian planets that are gaseous atmospheres or have gaseous atmospheres, and they are icy core planets. There's the obvious terrestrial and gaseous planets, which we all learned about when we were very young. But I do want to dig into exoplanets a little bit deeper because giving the same explanation every single time is a bit mundane. So there's more to the story than just 4 types of exoplanets. We can find a wide variety of planets that have more specific characteristics that differentiate themselves from the rest. Hot Jupiters, hot Neptunes, and cold Jupiters are different from the gaseous giants we see in our solar system and the ones we typically describe. And what all those types mean is basically the planet is either closer or farther from their suns than we usually see them, and they're lighter or puffier than we usually see them. So that's a slight subtype, or a couple of subtypes for some of the gaseous planets that are out there. They're rogue planets that are not gravitationally bound to their star and are somewhat isolated planetary mass objects. There are carbon planets, which have rocks formed of compounds of silicon and carbon. And then there are lava planets, which are larger and much denser than Earth, and they're very close in orbit to their suns, so they are very, very hot. And then there's another type of exoplanet, which is known as the ocean planet. And they're in the size range of Neptunian and super Earths, so somewhere between an icy core planet and a completely rocky planet. And they're likely to have some very deep oceans, as the name would suggest. We're talking hundreds of kilometers deep, though. And for comparison, the average ocean depth, according to NOAA, is under 4,000 meters. So for us to get anywhere near some of the numbers for ocean depths, we'd have to look to how deep our ocean gets at the maximum, which is the Mariana Trench. That's 2,500 kilometers deep. So a lot more than the average depth for some of these ocean planets, but closer to the number range than what we have on Earth, because Earth is like 1% of the planet is water and the rest is just rock. So that is the ocean planet in its full description. Unfortunately for us, despite all this knowledge we have of possible ocean worlds, we haven't found a planet that presently has bodies of liquid water on its surface other than Earth. But we might have just found one, and that's the premise of our first article today. Astronomers have discovered an exoplanet named TOI 1452b. The planet itself is orbiting a binary star located in the Draco constellation about 100 light years away. Now, 100 light years isn't too bad in the grand scheme of things. It's pretty close, but it is not amazing for exoplanets. It's pretty bad. Our closest exoplanet is Proxima Centauri b, which is 4 light years away from us. So when we're talking about TOI 1452b, that's like 25 times the distance from Proxima Centauri b, and given it's 4 light years away, it's already very difficult to reach. So, yeah, 100 light years distance is not going to make this exoplanet one we want to go to, but that's not the appeal. The appeal is more about the fact that it's an ocean planet. A quote from the article goes as follows. Quote, "The exoplanet is located at a distance from its star where its temperature would be neither too hot nor too cold for liquid water to exist on its surface. The astronomers believe it could be an ocean planet, a planet completely covered by a thick layer of water. This would make it similar to some of the moons of Jupiter and Saturn." So that's a pretty good sign. The exoplanet was found using many instruments and telescopes, including TESS, which predicted the planet was 70% larger than the Earth. Astronomers use an instrument called SPIROW or OU. I don't know how to say that aloud without spelling out the letters, but that is the instrument, and it belongs to the Canada-France-Hawaii telescope, based in Hawaii. So I'm going to call it SPIRO. SPIRO studies low-mass exoplanets in infrared, because obviously these planets do not emit as much light as, say, a star. They're mostly in the infrared spectrum or infrared part of the electromagnetic spectrum, so these instruments will be necessary. And so SPIRO is one of the instruments to do that for us. It studies low-mass exoplanets, and it had to study this planet for 50 hours to estimate the mass of TOI 1452b. So that's quite a long observation time. But there's even more to the process that makes finding this planet very difficult. They had to take the data that they got from this infrared instrument, and they had to analyze it line by line, which is literally the name for the method that they used. And they had to look at the host star's composition for clues about the planet's internal structure. So quite a lot of work that went into figuring out the not the nuts and bolts, but like, I guess, the nitty-gritty details about the planet. But we came to a conclusion that it's got some promise, and with this data in hand, the researchers had some amazing remarks. One of the quotes goes as follows: "TOI 1452b is one of the best candidates for an ocean planet that we have found to date. Its radius and mass suggest a much lower density than what one would expect for a planet that is basically made up of metal and rock, like Earth." So water could make up about 30% of the planet, which is 30-fold what the Earth has right now, which is really, really good. So that's a great discovery that has come about in recent times. That's our first article. So it's time to move on to our second article, which is going to be about Betelgeuse and its dimming that happened a while ago at this point. It started in 2019. So for starters, Betelgeuse is a M-type red supergiant star and among the brightest stars in the night sky. It's in the Orion constellation and anywhere from 10 to 20 solar masses, and it's also 10 million years old and 700 light years away. But more than this, Betelgeuse came into the headlines from about 2019 to 2021 due to the fact that it was dimming, and nobody knew why. A little bit of variability is not uncommon of Betelgeuse. In fact, it is known as a semi-regular variable and had changes in magnitude that were noticed like centuries before. So not an uncommon thing, but what happened in 2019 was nothing like we'd seen before. Betelgeuse blew 400 billion times as much mass as is usually emitted during a coronal mass ejection. from a distance, the sun's coronal mass ejections look huge. So the fact that Betelgeuse set, like, literally was like, hold my beer, watch me blow 400 billion times as much mass, that is a huge, huge amount of mass. You should, like, that it will be never expected of a star. And that led to a 60% decrease in brightness, or a threefold decrease in brightness, pretty much. In terms of magnitude numbers, it went from 0.5 to 1.7, which, if you aren't familiar with the magnitude scale, might sound like an increase in brightness, but it isn't, because the brighter an object appears, the lower the value of its magnitude on the magnitude scale. The scale is also logarithmic, so that a star of magnitude 6, for example, is 100 times brighter than a magnitude 1. So the change that we see in Betelgeuse here is a change of 1.2. If you work out the numbers there, the change would be 3.0143 times. So yeah, around about threefold, as I said. So this huge coronal mass ejection that created a huge decrease in brightness had astronomers worried, because, as we know, Betelgeuse, it's bound to become a supernova because of its mass. And so this event that happened led a lot of astronomers to believe, oh, it might be going into a pre-supernova phase. But then the star returned to regular brightness in 2020, so that kind of, muddied the waters a little bit. The theory about a pre-supernova phase kind of lost its merit, and we were just left with confusion. So it needed the help of observations from Hubble and other huge telescopes around the world to look further into what happened. And we figured out in the years to follow that it was a huge cloud of dust and gas emitted from the star that obscured our view of Betelgeuse and caused the dimming. So the consensus in 2021 wasn't completely formalized. It was sort of like the mysterious dimming was caused by a dusty veil shading the star, which in turn was the result of a drop in temperature on Betelgeuse's stellar surface. But then in 2023, and this is a quote from the article itself, using the Matisse, or multi-aperture mid-infrared spectroscopic experiment instrument, on the European Southern Observatory's Very Large Telescope Interferometer in northern Chile, a team of astronomers from France's Université Côte d'Azur caught the star before, during, and after the dimming event. Although the star as a whole appeared to darken, Betelgeuse's photosphere seemed to actually brighten during the event. The Université Côte d'Azur astronomers say these observations are consistent with a likely theory supported by observations that Betelgeuse dimmed from our view due to a burst of dust in the form of silicon monoxide coming from the star. In turn, that burst might be related to a sudden cooling of the star's surface. And so, yeah, that's a really, really long way of saying, all right, so we started 2019, 2020, not sure, but once there were studies kind of run on it a little bit, we had a sort of feeling that it was going to be, oh, there's something blocking our view, or there's something kind of obscuring the light coming from the star, and like there might be some temperature changes. And then in 2023 coming and being like, okay, so we saw Betelgeuse's photosphere, it seemed to actually brighten, so it looks like this sort of dust veil theory seems to work out, and it seems like the dust has, silicon monoxide, and there's a cooling on the star surface. So yeah, the dust veil sort of theory seemed to prevail. No pun intended there, if there was any. So that's the article. The consensus from the article in 2023 about their formalization of the theory in some ways was that if the theory holds true, it would also tie into the results of the 2021 study, as has sort of been implied by the chronological order that we've gone through with these articles and how this story has developed. So, yeah, we might have just reached a consensus with this 2023 article on what really happened all those years ago, it feels like, before COVID-19 and all of that. Anyways, I think it is time to transition into our last article of the day, which is about hydrogen-poor core collapse supernova. We've talked about supernovas before on this podcast, but perhaps a niche part of the subject is hydrogen-poor core collapse supernova. The name is indicative of the stellar object's physical characteristics, but not quite its origins. Its origins are a little bit mysterious. Hydrogen-poor core collapse supernovas consist of a massive star whose hydrogen is stolen by a companion star, leaving a hot helium core that evolves into a supernova. We used to think that these stars ejected their hydrogen envelopes, but that would make these objects way too rare for the frequency at which we might see them. However, on the other hand, even our current theory has only been verified by one binary system when models predict that 1 in every 3 binary systems create a hydrogen-poor core collapse supernova. And because of all this confusion, there's also like an alternative theory that suggests these stars form from neutron star collisions, perhaps, and even maybe neutron star black hole binaries. So, with that being said, a team of astronomers led by Maria Draut and Ylva Göthberg, hopefully I'm saying the names correctly, lots of European proper nouns in this episode. These two, they put all these theories to the test and tried to find an answer to these mysteries. So Draut, Göthberg, and their collaborators initially identified a group of several hundred potential candidate stars using data from the Swift Ultraviolet Optical Telescope. They then monitored a set of 25 of them for 4 years using the Magellan telescopes at Carnegie's Las Campanas Observatory in Chile. The properties of these stars were consistent with theoretical predictions of hydrogen-poor core collapse progenitor systems, including being hydrogen-poor, helium-rich, very hot, and part of binary systems. So, yeah, they've taken these sets of stars that or binary systems of stars that they believe might really fit into this description and this sort of evolution process or chain, and they've looked a little bit deeper into it. A quote from the article, kind of succeeding the previous one, goes as follows. They are hoping to find more intermediate mass helium stars in the Milky Way and other nearby galaxies, starting with this new promising detection technique. So what was the progress that was really made? Because it looks like there's a will, there might be a way. What are the steps from here, I guess is what I'm trying to say. So with this new detection technique that has been developed with these studies, we are discovering more evidence of a mysterious population of stars. The concept of a hydrogen-poor core collapse supernova lacks foundation, and if this continues to be the case, our theories will be completely invalidated. And, all the theoretical work that goes into this, we don't really want that to be invalidated. And another quote that kind of supports this is one from the author. This was such a big glaring hole. If it turned out that these stars are rare, then our whole theoretical framework for all these different phenomena is wrong, with implications for supernovae, gravitational waves, and the light from distant galaxies. This finding shows these stars really do exist. So in that sense, this study was a necessary step towards solidifying the theory of hydrogen-poor core collapse supernova. So yeah, that's pretty much all I got for the last article, and therefore this episode on recent happenings in the world of astronomy. Thank you all for tuning into this episode and making it all the way to the end if you have, and I'm assuming you have because you've come this far. And yeah, if you enjoyed this podcast episode and you're new here, then please drop a subscribe to see some more of this content. If you are on Spotify, then obviously that does not apply to you, and there will be a follow button for you if you've visited this channel for the first time and you want to see more. So yeah, that is all I've got for this week. Nothing much else to say. 3 lovely articles about some new stuff in the cosmos, and we'll be looking forward to 3 more in the next week. So until then, see y'all later. Peace.